Hello, this is Paul. Just going to take you through some of this presentation that we plan to do this morning, just to take you through some of the key elements of the UK electricity system, just to give you an overview and how the system works. Really want to focus on this bit of kit here, the package substation, and just really get to a point where you can understand what's going on inside and how they work. So this slide gives you a number of links. I'll send you all the links to these so that you can view them at your leisure. Again, these are all on YouTube. Really like this one down at the bottom here, which gives you a really good overview of how the national grid itself works, the national system works. So just take you through some of the key elements of the main electricity supply system in the UK. Starts at this end with production. Generally, we're talking about large power stations that are gas, coal or oil based, or things of nuclear power stations. They produce the power that's then placed into electrical cables and transmitted along through the national transmission system, which is at high voltage overhead cables. Then as it comes down into the regions, goes through either smaller overhead lines, overhead pylons, and then generally underground. Our networks are all underground cables on their way to the consumer at the final end. Just to take you through this slide, I'm not going to dwell too long on this, in that it's really just giving you an outline of some of the key terms that you need to understand electricity, starting with charge, which is the number of electrons. It's just a quantity of electrons in real respect. Current, which is the flow of electrons. EMF, which is the electromotive force, which is the push that's causing the electrons to actually move. And depending on what the component is that the electrons are moving through, you've got resistance and reactance that combine to give you impedance. Resistance converts the electrical energy into heat. Reactance converts it either into a magnetic field or stores the charge on a capacitor. Impedance is the most useful one that combines all of those three elements, R, XL and XC, together. They're all measured in ohms, but there are different elements of the same thing. And then finally power, which is the key thing, which we're trying to get work to be done at the end of our as the output of our system. Okay, so before we can move on to looking at how electricity is generated and how we can transform it, we need to understand some basic concepts relating to magnetism. You can see on the slide now we've got two magnets. In this particular case, the north and the south poles of the magnet are in proximity, and we end up with attraction between the two magnets. This is GCSE level physics. And hopefully you should be aware of this. If not, you need to go and do a bit of reading up on this. The opposite happens when we bring two like poles together, so north and north or south and south, and in this particular context we get repulsion. These two factors can be really useful for us when we can start to look at generators. So in the case of a coil or a piece of wire, because there's electromagnetic, as we pass the current down the conductor, a magnetic field is induced, which again can show as lines of flux around the conductor. If we then produce a loop, so we bend the wire into a loop, we can combine all of the individual magnetic fields to create one much larger one. It's still quite weak, but then if we bring more turns together, we can multiply by having more and more turns of wire the size of magnetic field that's produced. And if you can compare the magnetic field produced on a solenoid or a coil of wire, you'll see that it's very similar to a bar magnet, as we've got up here. And it's the same as the Earth, as it having an iron core, and as that's moving and rotating, it produces a magnetic field. If we then bring a coil into the presence of a permanent magnetic field, the interactions between these work in a similar way to this, in that you have areas where you've got attraction and areas where you've got repulsion, where the lines of flux are going to interact. This will cause the magnetic fields to deflect and to bow, and this generates movement where the coil will generally move in this direction, we'll move in an anti-clockwise direction on the positive, and a negative going in the opposite direction. We can use this to create movement. If it's fixed around a central point, the shaft of the output shaft of the motor, we end up getting rotation. Same could be said if we force the rotation, we can create and generate this interaction between magnetic component and electromagnetic fields. So how does this work in reality? Well, what we've got here is a diagram that indicates a permanent magnet in the presence of a coil, and we're going to show the interaction of this permanent magnet with respect to the coil as we rotate the permanent magnet in this presence of this coil. A real motor or a generator may be the other way around. It might be that we're rotating the coil in presence of a magnetic field, and it might be that we've got electromagnets, coils that are generating both. However, the principles are basically the same. The key thing being that we need rotation. So if we get rotation, you can see that as the bar magnet is rotating, a output is produced. This output is proportional to the position of the permanent magnet relative to the fixed coils. Key thing to note, it has to be through movement. If we stop the motor or the generator at any point, very quickly the induced currents will drop back down to zero. It's only as we move and rotate the magnet in the presence of the coils that we get an output. If we repeat it slowly, what you can see is as we get closer to the horizontal, we reach a peak output, and as we're moving away again at 90 degrees to the permanent magnet, the coil magnet, we end up with a zero. You'll notice also that I'm showing the rotation of the magnet in an anti-clockwise direction. If we were to do it in a clockwise direction, what we'd find is that the output would go anti-phase. It would go down first and then it would go positive. And this is quite important when we start looking at relative phase directions when we end up moving to three-phase systems. And it's also worth noting that this is for assuming a purely resistive load. As soon as we start getting any kind of reactance and impedance in the system, our phase angles between current and voltage will start to shift through 90 degrees or some other angle depending on the way the calculations come out. For our purposes, we won't go through that. Suffice to say, the output at this stage is just proportional to the position of the permanent magnetic field relative to the rotating magnetic field. So moving on from generation, we now need to start looking at transformers. So transformers are a device that's used to change the voltage and current levels of our power system. For reasons of power loss, it's much better to have very high voltages, which leads to low currents for transmission. Unfortunately, high voltages is not how our systems are set up in our homes. Our homes are set to lower voltages. And so as a consequence of that, in order to transfer and change the power characteristics of the energy being transmitted over large distances, we use transformers to transform the voltage up, and then transformers at substations to transform the power back down again and the voltage back down again relative to be connected and used with our customers. So if we look at what's going on in a transformer, what you can see is a primary coil. This is wrapped around the former of a core, and the core is made of material that can transmit the magnetic flux around from the primary core through to the secondary core. The secondary core, you can see, is not electrically connected to the primary in any way. It's purely connected via the magnetic flux. So as we input an AC wave at the primary, magnetic flux field is built up, and then it's destroyed and built up and then destroyed. And in doing so, the secondary will induce a current proportional to the size of the first. And in this particular case, you can see that there are many more turns for the primary than there are in the secondary. And what this does, using the equation over here, is that the ratio n between the number of primary turns and the number of secondary terms will cause a change in voltage. So in this particular case, we've got a large number of turns on the primary, a smaller number of turns on the secondary. It means that whatever voltage we put in at the primary, we'll get a much smaller voltage at the secondary. Conversely, current, you'll notice, is the other way around. Current of the secondary, current of the primary, the ratio is the other way around. And what this means is that whatever current we're putting through the primary, we'll get the opposing current, in this particular case, much smaller current in the secondary. Key thing to note is that the power, which is current multiplied by voltage in the primary, is equal to the power in the secondary. So if the voltage is going up, the current will be going down, or vice versa. And this is, of course, assuming that we don't have any losses in the transformer. There's none of the magnetic flux is dissipating in other directions, and so forth. In reality, there would be an amount of power loss in the system. Okay, so now we've looked at the sort of generation and transformer systems, we need to move and start looking at what's known as the three-phase system. Now, one of the problems you may have noticed with the single-phase system is that you only get power, maximum power, for a very short amount of rotation on the input shaft. When the permanent magnet or the fixed magnet and the rotating magnet are perfectly aligned. When they're at 90 degrees of separation, you get nothing. So one way we can get around this is by having a more complicated turn system, so that instead of having a single output, which is single phase, we have three. The three-phase system, as it's called, has coils at 120 degrees of rotation relative to each other. And what this means is that we can see that when one is at 90 degrees, the other two are at 45 degrees or 6 degrees rather, relative to the 120 degrees to that. So it means that one will always be getting power. So we've got two different ways in which we can connect it up. The first one is called the star, because it has a central point and three conductor coils radiating from it. The second one is what's known as a delta, and this is named after the Greek letter delta, which has the same shape. Each of these systems has their pros and cons, but going forward we need to just understand what's happening. So, as we rotate the coil relative to the permanent magnet, we can see that we end up with this kind of output. One, which is shown in brown, which we'll call L1, will be rotating, and it will initially be at 90 degrees relative to the permanent magnet, so its output is at 0. As it rotates through to 90 degrees, it reaches its maximum and carries on going from there. You can then see L2, which is leading L1, will be at will have just passed its maximum at time 0. L3, which is leading again by another 120 degrees, will now be at a negative, and it hasn't quite yet arrived at 90 degrees perfect alignment with the permanent magnet, so it's moving towards it. So you can see that as we gradually turn the shaft of the field, the coils, we end up with these three waves, all of which are the same shape, but all of which are separated by 120 degrees. One of the key things to note from this is that in the star configuration, the central point will always be at 0. This is the sum of all of the inputs. And if you look at this point, L1 is at 0, L2 is at a positive near maximum, and L3 is at a negative near maximum. So if you take the sum of these three values, you'll end up with 0. If we come forward by a certain amount of time, where L1 has now started to become positive, L2 has moving back towards 0 from its positive, you'll notice that the two of those added together equal 1, and L3 is now at a negative maximum. So at this point, the sum shown by green is 0. Come forward, and at each point as we go through, we'll see that the sum of all of the output of all of the waves at the central point are 0. Next thing to look at is two concepts related to the way that our networks can be connected up. As you can see on the screen now, you've got two real setups. The first one is the radial or spur setup, and the second one on the right is the ring. In the radial or spur setup, effectively each part of the network that's connected to it, so although it shows as plugs, we could equally look at this as being individual properties, is now connected one after the other to the live, the neutral and the earth conductors. Pros and cons to each of these. The big issue with this one, or the main advantage of this one, is if we have a break in the network, everything downstream of that point will be off, and as a consequence of that, we can find faults in it relatively simply. If we've got damaged cable, let's say at this point in the midpoint of the network, it's relatively easy to identify that between this point and this point, or this point and this point, we're going to be off supply, therefore we can be connected. Our LV networks are generally connected in this kind of form, where from the central location, either a point of connection or a substation, each way coming off is fed like this. It can go off in multiple directions, hence the idea of it being radial, in that it radiates out from a central point. If we then look at the ring network, you can see that it's very similar to a radial network coming out, in that it goes off in this direction. And when we get round to the far end, the last point in the network is then also connected back to the source. The advantage of this is, if we have a cut in the cable at any point, say for example at this point, this output, this load, will still be connected to the supply. It just be connected all the way around. The other advantage you have with a ring network is that because current can flow both down this route and this route to get to this location, we've effectively got two parallel conductors running side by side, and when we have two parallel conductors or circuit in parallel, the resistance of the two conductors is reduced significantly. So we can end up with a lot smaller cables to carry the same amount of current. The disadvantage of this is, if we do have a fault condition, it's much more difficult to find where the fault is. And if, for example, it was to cause the protection circuits at the distribution board to break, there's not a very easy way of finding that open circuit. Okay, so the final thing just to look at, part of this basic introduction, is just some of the main components that you'll see within a substation going forward. So what we've got up here is a basic fuse. This is the kind of thing you'd probably see in circuits or in a 3-pin plug. What all a fuse basically is, it's just a piece of wire. It's in a evacuated tube, so there's basically it's a vacuum, and what happens is, if too much current passes down that conductor, heat is generated, and if it gets too hot, the wire itself, the conductor, will burn out. The reason they make it glass like this is so that you can actually see it, and you can then see if the fuse itself has blown going forward. The ones we have in our substations are much bigger. Here's a fuse within a fuse carrier, and you can see the fuse actually then in situ, and it's a very much larger device, but it's the same basic concept, that it just burns out in the event of current being too high. So within a substation, this is the outgoing ways. So in this particular case, you can see that there are 3 ways that are available. Here you've got more. Here is our three-phase conductor, and so you've got L1, L2 and L3, and they're each connected with their own fuse. So there's three fuse carriers, one for each L1, L2 and L3, going out and then coming out at the bottom of the substation and going off and off to individual customers. When they're testing, so if we've got a fault on the network, what the fault teams can do is they can use this thing called a fuse mate, which replicates this but enables to be reconnected in a much more controlled way. And I'll send you the links through so you can have a look at what a fuse mate is. So that gives you a bit of an overview of the network. It's a little bit disjointed. I do apologise for that. I'll see if I can come up with a better way of putting this across. And but that's it. So hopefully you've got a bit of an understanding of the UK system now, the role of our network. We haven't really talked about licenses. I'll need to talk about that as a separate event, and some of the key terms used for electricity transportation.